My name is Ben and this is Design to Make. Today I'm going to be testing the 3D printed composite cross roller bearing that I made in the previous video to see to what extent it could be a replacement for an off-the-shelf all-metal cross roller bearing that would typically cost upwards of $1,500, with a goal to save at least $1,000. In the previous video we used metal roller bearings and a metal wire raceway to hopefully improve the performance and usability of the bearing. We'll see what effect printing it using a carbon fibre filled filament has on the performance of the bearing, and measure this in a number of ways using a test rig to give us as a meaningful set of results as possible. Okay, so last time I tried to measure the axial deflection of the inner ring using a dial gauge and my hands. I'm pretty sure I can do better than that, so let's design a test rig. Right, here's the bearing that we want to test. Let's add some reinforced brackets to hold the bearing securely and mount it in a wooden base. We're going to want to measure the flatness of the bearing at different angles reliably, so let's add a stepper motor with a belt drive. The only one I have to hand is a tiny NEMA 17 size motor. That should be powerful enough, right? I've decided the most interesting parameter to test is how well the bearing stands up to axial twisting moments and its axial runout, or in other words, how flat it rotates, as these are properties that are important for my use case and also one of the most unique strengths of this type of bearing. To test this, let's mount a rigid collet that we can attach a mass to one face of the bearing securely that will offset the centre of the mass at a fixed distance from the bearing. I'm going to use dumbbells of different sizes as the source of weight, and so we'll add a removable sleeve that will sit snugly around the smaller dumbbell, as you can see here. Okay, so we've got the first iteration of the test rig designed. Let's print the parts. Okay, so here's the electronic setup for driving the NEMA 17 stepper motor. The stepper motor is connected to the motor controller, which is mounted on top of a Raspberry Pi 4, which sends step and direction commands from a Python script running on it. The motor controller is also connected to a DC power supply to power the stepper motors. Two things that I think are worth pointing out. First thing is to actually run the program on the Raspberry Pi to control the motor. I've been taking full advantage of the recent released Raspberry Pi Connect browser-based remote desktop capability to remote into the Raspberry Pi desktop from my main computer. It's worked seamlessly for me and saved me time in countless ways, not least by removing the need to endlessly plug and unplug keyboards and mouse from the Raspberry Pi, and realised that it really can be as easy as copying and pasting between browser windows when you found the code snippet on your main computer and just want to add it to your program. For those who like to use the terminal to SSH in to control your Raspberry Pi or already use something like VNC, then I suspect you won't be quite so excited. But for everyone else, I'd entirely recommend giving it a go. The second thing to mention is that the stepper, like most steppers, is open loop, which means that there is no feedback mechanism to check if the motor actually was able to move to where you asked it to go. If I can't, say because it's trying to turn too great a load, it starts skipping steps or completely stalls. If you're lucky, it'll do this in a dramatic way and make a loud clicking noise and start shaking. But if you're unlucky, you won't notice that it's skipped any steps, and wherever you're controlling will just start not being where you expect it to be, which, depending on what you're using it for, can kind of be a big deal. Okay, first up, let's test the version 2 of the bearing that I made in the last video. As a reminder, it's printed using polycarbonate. We actually use Pushment PC blend and incorporates metal rollers and a wire raceway. Here you can see that I've zoomed in on both the dial indicator and the rotational angle that the stepper has been instructed to step to by the Raspberry Pi Python script. You can see here that the program moves 60 degrees, then pauses to allow the gauge to settle and rotates another 60 degrees. The dial indicator is measuring in millimeters of deflection of the inner ring parallel to the axis of rotation. The number on the dial is relative to the reading at 0 degrees. Where possible, I've tried to remember to zero the dial gauge before starting to take the measurements. However, for example, this time I forgot. First test is without any additional weight other than the hexagonal collet itself, which weighs around half a kilo. As you can see, the setup seems to be working pretty well. Okay, let's increase the load to 4 kg dumbbell. The idea is that it should fit snugly into the blue collar and then is fixed in place using the screws. This way the dumbbell shouldn't move around during the tests. Okay, great. We're ready to get this started. And we're off. There goes the program. 60 degrees, 120 degrees, but wait, there's a lot of noise. The bearing doesn't seem to be turning. Perhaps it's snagged on something. What if I tried to give it a little help to get it going? No, this isn't going to work. The motor just isn't going to cut it for this application, but it does nicely illustrate the downside to open loop stepper motors in projects where you can't be sure that you're staying within the maximum operating parameters of the motor. I guess I'll need to buy a bigger motor. While we wait for a bigger motor to arrive, I'm going to take the measurements manually by becoming a human stepper motor. Right, so that seems to be working for now. We can also measure the static deflection of the inner ring due to the weight increase. Looks like it's about 0.13 millimeters. While we're at it, let's increase the weight 8 kilos and take another manual measurement. Certainly more effort is required for this one. For 8 kg, the static deflection of the inner ring due to the weight increase looks like it's around 0.27 millimeters. Great. So despite the hiccup, we've got some baseline measurements for a polycarbonate bearing, which we'll go through later. As a comparison, let's try printing another bearing out of polycarbonate, this time filled with carbon fiber. As it should be quite a bit stiffer than just polycarbonate, this might give us some improved properties. What happens when you add carbon fiber to a filament? And why are there so many conflicting opinions as to whether it's a good idea to do or not? Let's zoom in on a region of a pure polycarbonate print. Each of these spaghetti springs are a polycarbonate chain containing repeating molecular units. These chains sit on top of one another in a big, tangled, relaxed mess, like spaghetti in a bowl. The ability of these polymer chains to be formed elastically and return to their original shape is an important property that contribute to making a plastic tough. You can say, hit it with a hammer, and it won't break. The important point here is that the plastic does move while it's being hit with a hammer, but when the force from the hammer is removed, it returns to its original position. So often tough plastics are also at least a bit flexible. But we're looking for a material that is as rigid as possible while still being tough. Now, one of the reasons that there are mixed messages on the effect of adding carbon fiber to a plastic is that there are 3 types of carbon fibers that you can add. Milled carbon fiber, which is very short carbon fibers, which is like adding watermelons to the spaghetti. Chopped carbon fibers that are long enough to be visible to the human eye, which is more like adding massive leeks or huge stale baguettes to spaghetti. And lastly, there's a continuous carbon fiber reinforcement that you can do, which is more like adding really thick rope to your spaghetti that is aligned to one direction. When we add a milled carbon fiber filament to the polymer chain, the chains have to move around the filler boulders or drag them along in the same direction that the plastic chains are being deformed in. As you might intuit, this makes it harder for the polymer chains to move, making the material stiffer to deformation. The polymer between the rigid carbon fibers has a larger local strain and stress for a given applied strain or load. As the load increases, the highly stressed polymer regions eventually fractures or separates from the carbon fiber, resulting in the material being more brittle. For milled carbon fiber filled filaments, this moderate stiffening combined with the reduced thermal expansion coefficient, which helps stop the part warping, are the 2 main beneficial engineering properties of a filament of this type, albeit at the cost of overall toughness. For the chopped carbon fiber filled polymers, and even more so for continuous carbon fiber reinforcement, this stiffness is increased to a greater extent, particularly along the aligned direction of the carbon fibers, giving rise to some of the impressive sound bites, such as being as strong as aluminium or black aluminium. To keep the comparison as fair as possible, I'm going to use a Pushment polycarbonate carbon fiber filament, which is filled using milled carbon fibers, using exactly the same print settings used for the polycarbonate bearing. Let's print it out. So our new large NEMA 17 motor has arrived just in time to test it with our newly printed polycarbonate carbon fiber bearing. Let's hope this does the trick. Let's test it with a 4 kilogram weight first to see if it can do better than the first motor. It's good so far. Wait. Oh no, it's still not enough power. I guess this means back to the digital drawing board, as we're going to need to jump up to a NEMA 23 size motor to give us the oomph that is required, as we're going to need a larger motor mount and a wider timing belt and gear assembly. Right, so the new NEMA 23 motor has arrived. which is more like the size of the motor you'd expect for this type of application. There are two changes in the electronics of this setup. Firstly, it needs a bigger motor controller for the increased power requirements. That's this guy here. And secondly, you might have spotted that there's a second cable coming out of the back of this stepper motor. That's an encoder cable, which takes us from a dumb open loop stepper and, with the help of the motor controller, turns it into a self-aware closed loop motor. So we should be able to run it at much closer to a maximum torque without any fear of losing steps. Let's get it attached to the test rig and try it out. Okay, I'm 100% confident that this motor will have enough power. Let's get going to make up some of that lost time. Oh dear, this time it's the timing belt that's slipping, and I can't put any more tension on the belt as the motor mount is bending. Okay, we're going to have to reinforce the motor mount. That's more like it. Smooth. Right, so now we've ironed out those creases, let's see how an unlubricated bearing holds up after, say, I don't know, 2,000 revolutions or 12,000 rotational moves with 4 kg weight. I tried to run the experiment with the 8 kg weight as well, but I couldn't stop the drive belt from slipping. I think it's an issue with how well the belt meshes with the large 3D printed bearing gear, but I ended up testing this the old manual way and once again became a human stepper motor. As you can see, turning this takes a serious amount of effort. I also tested the static load deformation for both the 4 and the 8 kilo weight for the polycarbonate carbon fibre. So we've done some tests. Let's see how the two bearings compare. Right, so let's look at some of the results. First of all, let's look at the axial deflection test that we did over the 1 revolution, where we took those 6 measurements every 60 degrees of how much the bearing was deflected with different loads. On the left-hand side, we've got the mean of these 6 measurements, and on the right-hand side, we've got the standard deviation, so how different they are from one another, how big the spread is. The first thing to note is that for both the 4 and the 8 kilogram loads, the mean and standard deviations are very similar. Basically no change for either polycarbonate or polycarbonate fibre bearings, which means that irrespective of material, they both have the same axial runout, which I think is quite interesting. Second thing that's worth noting is that as we increase the load, so does the axial runout, going from 0.1 millimeter mean deflection to 0.15 millimeters mean deflection. So here we're looking at the static axial deflection after loading. So when we add or take away 4 or 8 kilos to the bearing, we can immediately see that there's a much greater apparent difference between whether we print in polycarbonate carbon fibre or polycarbonate. When we add 4 kilos, the polycarbonate deflects about 0.13 millimeters, but when we make it at polycarbonate carbon fibre, it's only 0.07 millimeters that it's deflecting. And when we add 8 kilos, we can first of all see that the deflection is much greater at 0.27 millimeters for polycarbonate and 0.23 millimeters for the polycarbonate carbon fibre. So this corresponds to about a 45% decrease in deflection when you add 4 kilos of load and around 15% difference, much higher 8 kilogram loading. Well done for getting this far. So what have we learned? Adding carbon fibre to polycarbonate filament doesn't appear to improve the axial runner of the bearing. However, it does seem to reduce the amount the bearing twists when one face of the bearing is loaded, particularly for lighter loads. Given the amount of friction that is created in the bearing when it's loaded with 8 kilograms and the significant increase in static deflection we see, I'm going to conclude that 8 kilos of loading is too great for this bearing to be of any use. However, when loaded with, say, 4 kg, the static deflection was only 0.07 millimeters and the mean flatness was also around 0.1 millimeters, making this bearing design still in the running for real-world application, albeit one that doesn't require quite the same level of precision as an off-the-shelf all-metal bearing. And lastly, if a motor looks too small, it probably is. If you've enjoyed watching this video, then I'd really appreciate a thumbs up, like, or a click of the subscribe button if you'd like to see what I make next. Bye for now.